Okay, so today we're going to talk about equilibria. People are still coming in. And so last time we went over this pretty basically and just talked about direction of reaction and whether reactants or products were favored, which is pretty easy to do. Hopefully everyone's been able to master that concept. It'll be very applicable to next week's lab. So I thought I would just do a little bit of a review and show how solubility equilibria could be used to clean up a toxic water contaminant. And we'll be talking about a species of chromium called hexavalent chromium. Yeah, can we all quiet down? I know it's hard. I can't control the mic volume, unfortunately. So you can ask them the gentleman upstairs to turn that up a little bit. So hexavalent chromium ions are in the +6 oxidation state. Okay, you don't really need to memorize that, but that's what that means. And a particularly nasty hexavalent chromium species is the chromate ion, which is -2 charge. Now, the chromium itself is +6, but remember we have these 4 oxygens around it, so the overall charge is negative. Anyway, this particular species, like many hexavalent chromiums, is highly toxic to the aquatic environment. And it's due to its oxidizing strength. And if anyone's seen Aaron Brockovich, anyone seen that movie? Yeah, it's also carcinogenic, which is not good if it's in your drinking water or the fish is drinking water or frogs, what have you. So, yeah, sorry, it's cancer causing. For people that don't know that term, I should have helped from the front here. So the question is, if I want to remove this from the aquatic environment, obviously from water, where this thing's either leached into the water naturally or from industrial activity, and so we want to remove it from the water, and one of the ways to do it is perhaps to do a precipitation. Okay, so if you could selectively precipitate out chromium, then you could remove it from water, and then you just need to filter out that precipitate. So the question would then become, what salts could aid in the precipitation of chromium, this chromate ion, to remove it? To remove it from contaminated water. Okay, so that's a question, and we'll consider 3 salts. Potassium chloride, highly soluble. We'll get to that in a minute. We talked about one in a previous lecture, aluminum chloride, also known to be soluble, and one that's insoluble, aluminum hydroxide. And so really one of these is the best option to use to remove chromate ion of these 3. I'm not saying that's the best industrial process to remove it, but for the sake of discussion, one of these answers is correct. So KCl solubility is extremely favorable. Dissociates into the positively charged potassium, negatively charged chloride ion. We'll put a very soluble here. Okay, aluminum chloride, again, is pretty soluble. Again, that's going to dissociate into a 3+ aluminum ion and then 3 chlorides. Wouldn't say it's as soluble as potassium chloride, but it's pretty darn soluble. Aluminum hydroxide, on the other hand, which we've already discussed, is not very soluble. And when aluminum sees low pH conditions in hydroxide ions, it tends to precipitate. Maybe the better way of saying it is not very. Of course, some aluminum-3 and some hydroxide ions will be in solution, but most of this will be a precipitate. And just so everyone is aware, these are all the aqueous species over here on this side, because we're doing solubilization equilibria. Okay, so now we need to ask the question, so if we have these 3 salts and we have these reactions, these solubilization reactions, what's going to happen when they commingle with chromate? Okay, so chromate, potassium chromate, this solid is particularly soluble. Okay, so that would mean, I didn't put these down, but for people that are wanting to keep track, it's pretty soluble. This is going to be a highly favorable reaction. We'll dissociate to 2 potassium ions and 1 chromate. But on the other hand, aluminum, and now we need to balance the charges here, aluminum chromate is not very soluble. So this is where you guys get to come in. You get to answer the question, what salt would you now use given all this data? So it's relatively insoluble. So back to the original question. I hope I can fit all this information on this view here. Of these 3 salts, KCl, aluminum chloride, and aluminum hydroxide, who would pick potassium chloride? Anybody? You guys watched the webcast from Wednesday? Okay, who would pick aluminum chloride? All right, good number. Any peer pressure to jump on that bandwagon? Okay, who would pick aluminum hydroxide? No takers? Which would be best to use to clean up and remove a chromate ion from contaminated water? Okay, so the correct answer is aluminum chloride. And the reason is that first and foremost, you need to be able to get your precipitating ion into solution. And the best precipitating ion that I've shown you is aluminum-3. So aluminum chloride is a good source of aluminum-3, and that aluminum-3 will then combine with a soluble chromate ion and bring it out of solution. Okay, so that is the trick. So that's a good example and an excellent kind of exam question that really summarizes this. So now we're going to do a calculation, again using solubility equilibria, and be a little more quantitative. So we're going to define solubility in this particular example as the number of grams of this salt, which is calcium fluoride, that can dissolve in 1 liter of water. Okay, it's a pretty straightforward definition. So this is going to be in units of grams per liter. Okay. So we have this reaction, and again we have a solid going to 2 aqueous ions, 2 fluoride ions. Fluoride's a halogen, -1 charge, so you need 2 of them to balance, +2 charge calcium. Now its equilibrium expression for this solubility product, that's what the S and the P mean. Now hopefully people can see, first of all, you're doing a solubilization equilibrium reaction, and you see the word product, and that gives you the answer to what this expression might look like. It's a product of the concentration of the calcium ions and the fluoride ions. But there's one trick there. Remember that there are these exponents on these different concentrations in the solubility product. And just to give you a heads up, you can see that the 2 exponent comes from the stoichiometric coefficient of the fluoride ion. Of course, there's a 1 here hidden in front of the chloride, and then there's also 1 here, but we just don't show those because, yeah, we don't do that. All right, and that is 4 times 10 to the minus 8, this particular solubility product. And so when you see a number like this, you know that this number is much, much less than 1, and that would tell you that calcium fluoride is or is not soluble. Who thinks it's soluble? No one should, right? It's not soluble, not very. But, we want to go beyond this, and we want to solve this. We want to use this information to determine the solubility. So we want to use, the KSP expression to solve for solubility. This is what you typically would use this for. Okay, so, well, it's not really a question. Okay, and so the key here is that, there's 2 fluoride ions and 1 calcium ion per calcium fluoride. So that would mean that if we took our KSP, 4 times 10 to the minus 8th equals x for the concentration of calcium times 2x squared. And unfortunately, I'm sorry I did that to you, but for the, sometimes it's not so cool how it draws circles. And that's for the concentration of the fluoride. So remember, we have 2x and then squared. Okay, that's the key. There's 2 places where that 2 comes into play in the algebra. So that's going to work out to, 4x cubed. Okay, so we can quickly, without doing much effort here, we can quickly cancel the 4s, but we're left with this sticky problem of a cube. And as I told the previous class, I should have made this 4 times 10 to the minus 9th and just lied, so I didn't have to use a calculator, but we can probably use a calculator. And it is a good time to talk about calculators, actually. So for the exam, you need a very basic calculator. It does logarithms and cube roots and natural and base 10 logs, but it doesn't have memory and all these other things. So you need one of those types of calculators for not just this class, but many other courses that you'll take at Berkeley. We can't let you use your cell phones, I'm sorry, because they have obviously web access and everything else. But if you take the cube root of this, then you'll end up with this value, okay? And this is, I did that wrong. There's another 0 in there, I'm sorry. And so it's about 2.2 millimolar. And remember that these units are molar. So don't be confused on an exam with the wrong units, because remember the question asks you, well, what is this? What is this thing in units of grams per mil, or grams per liter rather? So that's pretty straightforward. So this is 0.0022 moles per liter. That's what molar is. And then we need to multiply this by the molecular mass, which is 78.1 grams per mole. And this is, of course, the molecular mass of calcium fluoride. Okay, and we do that, and then we get the true solubility. We might want to just write grams of calcium fluoride per liter. So the true solubility, in terms of what the units that we requested in this particular exercise, is about 17 milligrams per liter. Okay, it's not very soluble, considering lots of other salts can get hundreds of grams. Yes. So, the solubility units are no, and I mean, you could say what's the solubility in molar. You just say whatever units you'd like it to be. Yeah, so some unit of either mass or some unit of moles per liter. So yeah, just be sure to look at the instructions on the question before you start diving in. All right. So now we're going to do an acid-base equilibrium, and so we're going to take this to the next level. And we initially talked about solubilization, and now we're going to talk about ionization, or proton ionization, or proton dissociation. And I thought we would use our old friend terephthalate as an example. Might not be your friend, but so terephthalate. We've done this one before. Okay, so that's terephthalate, it's -2 charge. We're going to abbreviate that terephthalate TPA 2-. Okay, that's going to be our abbreviation. If we add a proton to that, we would get a protonated form. Okay, and we're going to call that H TPA 1-, or just minus with a circle around it, however you want to do it in your notes. Okay, so that's actually a proton. This is a proton association reaction. Okay, that's a proton association reaction. It turns out that, as you can see from the title here of this slide, that we're interested in the acid dissociation constant. And that's the convention that most chemists and biochemists use when they deal with acid-base equilibria. So if we're going to write this as a dissociation reaction, write as a dissociation. You just write this in reverse, but I'm not going to write out the structures anymore because they're not really going to help us. But that would be this protonated form, singly protonated form, going to a proton plus the completely deprotonated terephthalate ion. And this reaction has a equilibrium constant associated with it we call the Ka, and I'll get to that in a minute. And the Ka, these are all aqueous ions. So all aqueous ions, so they all have to be represented in the expression. No, minus. Okay. All right, so that is the acid dissociation constant. And this A means That means acid, okay? That's what it means. It does not mean association, okay? And we don't put Kd for dissociation, we put Ka, or acid, okay? Turns out for this particular ionization, we're talking about 4 times 10 to the minus 5th, okay? And so we can use that if we knew what the proton concentration was, and we could determine the ratio of the completely deprotonated terephthalate ion and the singly protonated version, okay? So if we assume a given proton concentration of, in this case, something easy, 10 to the minus 4th molar, then we can ask, what is the ratio of, say, TPA 2 minus over H TPA minus, okay? So I've written this out in a way just so we can do a very quick and dirty calculation, and then we'll be able to use this data later in plotting some of these results for this particular ion to build up a titration curve. So we know that the Ka is 4 times 10 to the minus 5, and we know that the proton concentration is, and we know that then we're multiplying this by this ratio, and I've written out the ratio in a useful way. So if you divide these two out, you'll come up with a ratio, okay? So 0.4 is equal to this ratio of TPA over HTPA minus. Okay. So you always have to ask the question whenever you do a calculation, does this ratio make any sense? Whenever you do a calculation in chemistry, physics, whatever, when you go to Home Depot to buy 2x4s and make shelves, whatever, you need to ask yourself, do I need 100 2x4s or 1 or 2? Yes? Oh, should there be a 4 before? Should the hydrogen concentration be 10 to the minus 4th? Oh, that's a mistake. Yeah, you're right. Sorry. Yes, it's 10 to the minus 4th. It's just, okay, pH 4. We'll get to that in a minute, but yes, you're right. That's how you end up with getting 0.4. Okay. Yeah, thank you. So yeah, now this ratio makes sense, right? Yeah, so, but really, even without the math error, you need to ask this question, of course, should there be more protonated TPA than TPA, 2 minus, or terephthalate ion completely deprotonated? Well, yes, there should, because the pH, the proton concentration here, 10 to the minus 4, is much, much larger, or larger than the acid association constant. It's very easy to remember. The proton concentration is greater than the acid association constant, so yes, the protonated species is favored over the concentration of the completely deprotonated form. And likewise, if the proton concentration were much less than the Ka, then it would be the other way around. And if the proton concentration were equal to the Ka, then you'd have an exact balance of the two. And we'll get to ways of doing this a little more easily in a minute, but that's acid-base equilibrium in a nutshell. And so people don't really like to think in scientific notation, as I just fumbled around with it there, for the proton concentration. Instead, we've devised a scale called the pH scale, where P means power, and the pH scale is a log scale. Yeah, power. pH scale is a log scale for the proton concentration, okay? So the definition is the pH is equal to minus the log of the proton concentration, okay? And so it's a very convenient way, of reporting, H plus, much more succinct, right? Like I said, if I had a proton ion concentration, okay, if H plus is equal to 10 to the minus 4th molar, then this is straightforward because I would take this proton concentration and take the log of it. The log of 10 to the minus 4th is equal to, and minus that, is equal to the pH, okay? And for people that know tricks about log base 10, of course, log base 10, you just move the exponent down, minus 4 times minus 1 is plus 4, and the log of 10 is 1, so it's, pH is 4. Okay, remember it's plus 4. So in any case, it's a very convenient way of reporting the proton concentration. And the other useful thing to do is to convert your, we can similarly convert our Kas to pKa values. Okay, so people often ask you, well, I'm using this particular, acid, like weak acid, weak base, or weak acid, let's say acetic acid, and I know its Ka is about, its Ka is about 4.5, 5 times 10 to the minus 4th or something like that. Okay, well, what's its pKa? And generally, people like to talk about it in terms of pKa, and we make a similar sort of calculation minus the log of the Ka. So, let's go back to terephthalate. Its Ka is 4 times 10 to the minus 5, so its pKa, straightforward, minus the log base 10 of 4 times 10 to the minus 5, which is equal to 4.4. Okay, there's some rounding I've done there.